Lab 5. So the purpose of this lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil, to model the magnet-tube interaction computationally, and to compare your computational predictions with your observed data. The principles used here were Faraday's law, Lenz's law, the magnetic field of a wire, and Newton's second law, and the results were that the computer model roughly aligns with real-world observations, but there is plenty of error in there. So for the experiment, the system was the bar magnet, and the surroundings were the aluminum foil tube and Earth. The initial conditions were magnet falling from rest. The procedure followed was to mark the north pole of the magnet, then find the mass of the magnet, measure the width, internal radius, and length of the tube of aluminum foil, drop the magnet through the tube 5 times while recording the time, and find the average time it takes for the magnet to get through the tube. So for the results, the tube was about 0.3 meters, the width was about 3/4 of a centimeter, the internal radius was about 1.5 centimeters, the magnet was just under 1 kilogram, and the dipole on the magnet was 7.729. And here are the observed times, and here's the average time. So for the code, here is the magnetic field of the magnet. Here is the flux going through each of the rings. Gravity. This down here is the B field of each ring. And this is the total net force. So, for the model, this is what you got. Follows mostly quadratic until it falls out of the tube. And so the magnetic force acting on the bar is constantly increasing in this case if the velocity is decreasing. And then to get the computer model a bit closer, remeasuring the magnetic dipole for the magnet would help, because I didn't use the same magnet and therefore you can't really assume the same dipole. And other than that, there was also error in timing, and the magnetic bar was pretty heavy for the tube. So for the what-ifs, if the resistance in the metal was decreased as much as possible, the induced current from the magnet in the tube would increase. This would increase the induced magnetic field in the tube, slowing the descent of the magnet. And if you cut holes or slots into the tube, you would get less current induced into the tube by the magnet, which would have the opposite effect and cause the magnet to get through the tube faster.